Good morning everyone, welcome back to our channel, and let's continue with our tutorial course, let's call it by its rightful name in Italian, on lathe programming for CNC, lathes. I had told you that we are close to using simulators for the actual programming, but I mentioned that I would invent something, and indeed I have to disappoint some of your expectations if you thought we would start programming today, because I was overlooking something rather important, namely the offset settings, the tool zeros, and the virtual point of the tool. Let's discuss this. Every tool, every machine, when you set it up, is a hollow self-centering device and a completely blind turret, meaning the machine does not know how to move in the space it has available. You set up the self-centering device with clamps, but the turret, especially the one we are interested in at this moment, is set up with tools. What does this mean? If this is your turret, viewed from the side, you will mount here. Let's pretend we have a VDI, a small insert, a round tool, okay? The turret does not know if this round tool protrudes 30 millimeters, 10 millimeters, or 100 millimeter from the turret, and it does not know the exact distance between here and here. Let's say that the indicated distance is fairly standardized, but the machine does not know that. So the turret is set up with tools mounted, so to speak, at random. We will not leave anything to chance. We will ensure that the tools protrude as little as possible. But if this is our self-centering device with our workpiece on it, and here we set the work 0, the machine will not know this distance, and therefore these two coordinates, and the distance in x. It is up to us to tell it what this distance is. Well, how do we do that? The luckiest ones, those who work with fairly recent machines, produced in the last 10, 12, 15 or even 20 years depending on the machine model, will have noticed that there is a sort of little arm here. A little arm that descends and brings approximately to this position a cross-shaped probe, where we usually have written x plus, x minus, z plus, and z minus. What does the operator do? It enables the hand wheel with the job buttons and goes to probe all the tools mounted in the turret, here and here for the externals, here and here for the internals. If it has any boring tools that work in pull, meaning going backward, it will also probe this area. So an external tool will be brought to probe here, and the machine will emit a beep. And in the tool table there will be a page of yours that will have a sort of table like this, TO1 for example, X, Z and R. The machine will automatically input numerical values here, while the radius of the tool will be entered by you, 0.8 for example. Those numerical values are needed by the machine to perform calculations based on the values that are known to it. For example, the machine necessarily, if we have our spindle connection here, self-centering connection, knows the distance between this point and the center of the turret, because these are data from the manufacturers. It does not know which self-centering device or clamps we have mounted, but from the moment we go to establish these two values, and it does so through this little arm. The machine goes from being blind, from not seeing, to being a seeing machine. Why? Because for each tool, it knows that distance. At this point, what do? Let's take just one of these tools. We will perform a chamfer, and we say that is my Z0, so my axis origin. The machine that knows the distance between here and there for all the other 12 tools is smart enough to make complex calculations and learn the offsetting point. Every tool mounted in the turret, this is the concept of the arm. If you are lucky, if you are a bit less lucky, you have to do one thing. No, we can leave this. It's a slightly more laborious task. You don't have the arm because your machine is old, or also because it has broken, because the arm can break. Even one does not work, because the arm cannot break, because the arm is broken. Then you have to do the machine zeros, the old way. What do? Let's take this work area, transfer our piece here. In this specific work area, the self-centering chuck is rotated manually and precisely, so there will be a control area dedicated to entering our codes manually and carefully. We will write on a command line of our lathe machine, M4, S300 G97. This is done, for instance, when operating at fixed speeds by using the manual hand wheel. You move the tool into this area and perform turning by moving carefully along the Z-axis direction, meaning never moving along the X-axis. At this point, you will have almost approximately obtained a diameter. This is our newly created piece. This diameter will be measured accurately. Let's say we measure 50.3. We will go to the tool table and tell it 50.3. And we press a button. Normally on Fanuc, the button is measure. It will convert this 50.3 into the dimension it needs to have this, the distance between here and here. Okay, the same process will be done in Z. You bring the tool up here, make a chamfer. In Z, go back up and tell it Z 0.5. It depends. We have to establish that ourselves. Z 0.5 measure, and the machine will write its value or the dimension it will need here. Now, however, we have a turret with 12 tools. Do we really have to do this for 12 tools? Generally speaking, yes, we have to do it for all the tools. The problem is that if our Z0 is here, if we go to chamfer the piece, or if we are very careful about how much we chamfer, we will touch. And then we move to the 13th. Or we can use the little trick with the sheet of paper. So excuse me, let's do something. I didn't want to do this. The little trick with the sheet of paper. I'll show you here. This is it. We take a sheet of paper, you see? Let's stop for a second. You see that I'm sliding it up and down. And at a certain point, you'll see that the little sheet no longer slides. Well, I was doing this with one hand, but I'll show it again. It's quite simple. Little sheet, tool, workpiece plane. You see, this is our piece. I am on the workpiece plane. It has already been turned. I approach with the tool and go up and down with a torn sheet of paper until the paper gets stuck. Well, this is my piece. This is the tip of my tool. I put a little sheet here. I have a dial set to hundredths or tenths, no more. I go up and down with the little sheet and give a little hit of 0.05 in Z until I narrow the distance between here and here to a sheet of paper. When I touch the part that I have turned with the previous tool, I know I am at ZEROES. So on T2, I will write ZEROES and then measure. And the machine will calculate the distance in the tool table. I can make the same statement above, saying that it is at 50.3 when I go to touch it. Okay? The same goes for the boring. Tools. It becomes a bit more complex because you still need a tube or a square. If I know I have turned a diameter of 50.3, I place a square here and touch the square with the boring tool. This is not the most precise way to set the zeros. The best way is obviously to have the caliper. The most precise method is to turn and measure. The tricks are the sheet of paper and the square. However, this way we will be able to tell the machine where it is located. As for the tips, the X is set to 0. So the X distance is set to 0 and automatically the tips are at 0. Provided that the machine is properly squared and aligned, meaning the machine geometries are correct, and accurately calibrated if the machine has taken a hit, and the turret has shifted by approximately 3/10 of a unit, in the coordinate system we will need to write x 0.3 or x minus 0.3, and this is the knowledge you need to have about your machine and ensure that all components are functioning optimally. Okay, that said, the first thing to look at is the comprehensive tool table for further inspection and verification. Let's take a look at it for a second. We can close this as we no longer need it. This unappealing component we put here for better understanding and clarity, so I set it up. You see this button? This is my tool table. You see, now it's not all there. This is a simulation environment which is used for training and testing purposes, so it doesn't have real distances. However, this is initial position number 1. In the sequence, this is the specific tool we have currently mounted for this operation. This is the measured length in the x-axis dimension. This is the measured length in the z-axis dimension, and this is the precise radius of the tool as per specifications. Okay, now if you know that, honestly, it leaves me somewhat puzzled and uncertain about the exact implications. Fanuc, on the other hand, has 2. It also has the offset feature as well, which is crucial for accuracy. Anyway, by modifying these lengths, the gradual wear and tear of the tool's radius is also modified over time. What does that mean? If I have a profile and I work on it, so I use the tool once, twice, 3 times, my tool will gradually lose its sharp edge and effectiveness. It wears out when compared to its original 0 point or baseline. From here, there will be a measurable distance of precisely 5/100ths of a unit. I say 5/100ths, so it means that the next time this piece comes back, it will have a diameter that instead of being 100 will be 100.15, 5/100ths radially. It incrementally grows by 1/10 of a unit in diameter. Therefore, the critical importance of the offset is to add a coordinate system that is directly related to the precise tip of the tool in machining operations. What am I going to write in my offset? In my offset, I will write calculate 0.1. It will shift relative to its reference axis, that is, the tool 0. It will move the 0 we set by 1/10 downwards, and it will return to turning at 100 mir. This is the offset discussion. In programming, knowing nothing is not useful, but not knowing what the tool offset is, I would say, is sad. Instead, what concept should one have during programming? One must have the concept of the virtual tooltip, and I would say this is quite important. Let's take a good zoom on the tip of our tool. The tip of our tool will appear like this, and here we will have the tip radius. Let's say we have a tip radius of R0.8. What does it mean when we go to touch our famous cross-shaped probe? and we wonder about its significance. We will touch it meticulously at this point, and exactly at this point, so the tool. Therefore, we can never exactly zero the actual tip of our tool, but a virtual tip. Similarly, if we are going to turn, we will return with this contact area to the cylinders, and we will chamfer with this contact area. So what we will have zeroed is this point, a point that is in the air, meaning it does not coincide with the actual part of our tool. This means that when we go to program, we will always program relative to this point. Therefore, if I need to make a chamfer, okay, I will rest my tool here, then I will move up. This, you see that I go up to here because I give it a diameter of X. Then I move to approximately 45 degree angle. This is still the virtual tip of our tool. If I go to join the tangents of the two tool radii, you will see that my turning, if this will be 245, my path will be this. It would indeed need another color. Let's see. My actual path will actually be this one. I am adjacent, but here I go up. So all this part of the metal will not be removed. So my chamfer 2x2 will no longer be 2x2, but will be, for example, 1.7417. The concept of the tool's virtual tip. So you might ask why this also applies to a rounded profile. Here, my tip will never be in contact, but a virtual point will be here too. So my rounded profile will never be exactly the same as what the designer had planned. The error is greater, the larger the tool radius. You understand that if I have a tool radius of 0.4, I will be here. If I have a tool radius of 1.6, I will be here. And so, the larger the tool radius. It seems like a joke. Let's hope YouTube doesn't censor me. The larger the tool radius, the more important it is to keep this concept in mind. So, if I have a radius of 1.6 and I program a chamfer 1 by 1, the chamfer will not be made. Fortunately, we are working with CNC numerical controls, so the trick, yes, the trick is called tool radius correction. Tool radius correction is done with 2G codes, G42 and G. G41 is inserted before a profile, so you create the profile and then forcibly disable it with G40, whether it is G41 or not. G42, what is the difference between the two when I follow a profile in this direction? That is clockwise. I use G42. When I follow a profile in a counterclockwise direction, I use G41. It follows that normally G42 is used for external profiles and normally G41 for internal ones. There are also some more particular cases where using G42 and G41 can be problematic. You always see that after G42 and G41 Most machines, not all, some more intelligent ones, only foresee the use of G1, so you cannot move quickly in radius correction mode. Another thing is that you cannot program a radius of 0.4 if you are using the tool radius compensator at an angle, as you see in a corner like this. So here I have my tool. If I have a radius of 0.4, my tool in the tool table specifies that it is a radius of 0.8. The machine will generate an error because it cannot absolutely create a radius of 0.4 not from a tool with a radius of 0.8. Okay, it's different if I instead have a radius of 4 here. If I do it without tool radius correction with a radius of 0.8, it will come out as 3.2. If I actually go to correct with G40, in this case, G42 will give me a nice radius of 4 without any ifs or buts. Another thing is that when working in G41 and G42, it is necessary to attach to the piece. That is, if I have a piece made like this, I move quickly, and the approach distance should always be at least twice the tool radius. That is, I arrive in G0. At this point, my physical piece is here. I have a radius of 0.8. Let's say I bring it to Z2. I set G042 and approach giving both coordinates X and Z because the machine, when I set G42, shifts. I give both, then we will do some examples, and don't worry, I give both and the machine does not generate the error. If instead I approach to 0.5 with a radius of 0.8, the machine does not have time to make the correction. There are people who lose half a day with these codes because they are poorly digested, often giving small alarms because I managed it incorrectly. When I detach from the tool, I must detach properly. I cannot detach by a tenth when coming away because it is a correction to a tool radius above the quota. So the first times, don't worry if the machine gives you errors due to impossible tool radius correction. Let's see a practical example. What is this then? Let's go back to the program. We have created a program and we are going to simulate it. As you can see, in the simulation we have a green path and the workpiece, a green path that is detached from the piece. Now in my program I don't have a G0, but I have a G1 without any tool radius correction. I used tool 01, which is a tool that has a radius of 0.4. Let's absurdly set a radius of 5. Do you remember what our piece looked like? If you don't remember, we will do it again several times. Look at what happens with a tool radius of 5. Oh, sorry. I sent it. So, okay. Simulation. Let's hope it doesn't trigger the new send alarm, because if it does, I have to re-enter it. Syntax error. Let's completely delete the block. I select the tool. Okay, having pressed it twice, I inserted it twice. Here you can see that it creates the chamfer. Obviously, the point it calculates has moved away. The chamfer is there, but physically there is no chamfer here, and this has become smaller. Let's review it. Let's set it back to 0.4. go back to the program and simulate it. You see that? Now the chamfer is there. Perfect. Let's go back to edit. Go after the G0 and insert a G42. Then we go here and insert the G40. Let's simulate. Okay, now let's change the tool radius. So in the offset, we set the radius to 0.8. We simulate. You see that my green line moves away, but the profile remains the same. Let's go to the offset and set it to 1.2. Sooner or later, it will trigger an alarm, of course. So, in the simulation, if you look closely, this very precise simulator also increases the tool radius. You see that this distance increases, but the profile, in this case, remains the same. Let's set the offset to 2.5, which is not a standard radius. But let's see if it finally gives us an alarm. It does not give an alarm, and the profile remains the same. So what radius do I have here? Edit. I have a radius of 5 and a radius of 2. Let's see, Z45, radius 2. Let's set the tool to a radius of 5.5. Program Manager example. Simulation. Let's see if it should give me an alarm. However, not all programs work the same way. Here, it simply limits itself to getting the radius wrong because it can't do it. But you see that this radius has remained. This, instead of FANUC, would have returned an error because it would have said, no, I can't do this radius for you because it exceeds what you are asking for. Let's exaggerate. With a radius of 10, here it is. You see, it managed to correct itself here, but obviously here it couldn't correct the radius of 5. It did it from 10. I prefer a FANUC that gives you an error. Now we will remove G42 and G40, and we will see. What a horrible profile that the machine will create, you see. All the chamfers are missing because with a radius of 10 it is not possible to make them. Chamfers are crucial for ensuring the edges are smooth and meet design specifications. Okay, I hope this concept of virtual radius is clear. The virtual radius is an abstract idea that helps in understanding how the tool interacts with the material. The tool, what matters is learning to use G42 and G41, which are essential for compensating the tool path. Many real operators, those we find in workshops, ignore this concept due to a lack of training or understanding. So what do? They reason like this. I have a chamfer of 2, but without understanding the underlying principles, they might make errors in the final product. For 45. To be tackled with a radius, insert of 0.8. Instead of putting C2, I will put C2.8. Okay, I have a radius of 1. To be tackled with an R08, I tackle it with a radius. It is no longer possible to work like this. It is no longer possible to work like this for a reason, for a series of reasons. 1. The required quality is no longer the rough quality of the past. We have measuring machines that are more precise than the machines that produce the parts. So in the technical office, sooner or later, the mistake comes out because it is not a mistake, but don't become dramatic, because then you bring it to the technical office and they tell you this chamfer is not 2, it's 2.2. Fix it. It wouldn't change anything, but if you work with the tensile radius correction, the chamfer of 2, C2 becomes C2, and that's it. 2.8 relatively becomes 2.8. That said, in the automotive industry, chamfers are no longer chamfers. Chamfers in automotive are now complex profiles, meaning in the drawing they quote you 2.2. But then, in reality, in the title block you find writings like sharp edge 0.1, so what does that mean? It means that here you have a chamfer of 245, but here and here you have two radii of 0.1, and the radius of 0.1 you make. It 0.1. It is the radius of 0.1 that you make. Only with tool radius correction 0.15 or 0.2 can you remove the bars, so you must learn to make finishing profiles. Roughing is not necessary, but finishing profiles must be done with G41 and G42. When it's not possible, CAD/CAM can help us, direct programming can help us. For example, we will see something about direct programming where once you have entered the tool radius in the tool table, it takes care of it, but do not think you can ignore G41 and G42, because sometimes they are annoying. Just by increasing the C, increasing the R, or decreasing them when working on the inside, you will not be professionals in the field. I hope this concept has come across. I remind you that on my channel there is an older tutorial related to the Fanico where these concepts are revisited in a different way. This does not mean that I did them wrong today or that I did them well. It means I have two slightly different approaches to explanation. Since these are important but difficult concepts, not difficult to understand but to convey, the problem might be that I struggle to explain it to everyone. Some will understand it immediately, while others may need some additional explanation. On my channel you will find another video made on the board dedicated solely to the virtual point of the tool. I recommend you go look for it, watch it, and integrate it with today's explanation to fully understand this concept. I thank you for being with me today, and I look forward to the next video. Like, share on social media. Go to your store and say, oh, there's an idiot who does. Show the video to others, we can have a good laugh, and maybe someone learns. And even if 1 in 1,000 learns, I am very happy for you. Thank you, and see you next time.